Welcome to our booth for simulation use case 3. In this presentation, we will focus on Lidar simulation and how we use Lidar simulation for a component test in an open loop setting. Briefly about the setup. So we have an environment simulation. Could be IPG CarMaker, could be DSpace ASM, any tool who provides the environment and a rendering engine inside this environment, for example, ray tracing. And via the OSI interface, we connect our model to the environment simulation and get moving and stationary objects as ground truth, and also rendering results from, for example, ray tracing. And then we connect our LiDAR detection model, where we compute detections out of these rendering results. And then in a third step, we have a tracking simulation, which is our system under test in this use case. So we would like to compare the tracking to ground truth objects to evaluate how good the tracking is. In more detail, we have a unified modular modeling framework for our model, where we again get as input the object and the rendering results. And then in the first step, we do the detection sensing, where we get all the ray tracing results and compute a raw signal per beam. And on this raw signal, we perform thresholding. We're capable to generate multiple echoes per beam, get the intensity. We can also compute echo pulse width, as some real LiDAR sensors provide this as a substitute for intensity. And then in the second step, we bring the detections we got from that into the eco vehicle coordinates, being able to also perform sensor fusion, for example, if we would have multiple LiDAR sensors in this step. And then as a system under test here, we have segmentation, object detection, and then a tracking algorithm providing an object list as an output. So we have the detections, what we know as a point cloud for LiDAR as an output, and the moving and stationary objects that are detected by the LiDAR sensor. And as an example, we see here in grayscale the reflections or rendering results. That's the green on the tool and the left. And on the right, that's our modeling input. And the colored dots are then the individual detection points from the point cloud that we compute in the detection sensing step. And on the object side, we of course have the ego vehicle marked in red. We have our ground truth objects, they're marked in green here, and we have our detected objects in blue. This is, again, the output from the model, what the tracking algorithm came up with. And then now we can evaluate these detected objects. Here in video form, we can just inspect visually how they line up with the dimensions, with the positions, with the ground truth. But of course, we can also do computations on these, because every time step we get position, the entire pose, velocity, and so on for these objects. So we can employ metrics. Simple one is intersection over union. So we simply look from different perspectives on the ground truth and on the detected objects and see how much they overlap. And then we can calculate this as one metric to show how good the object detection and tracking algorithms are. We can do this from a front view, from the LiDAR perspective. We can do this as side view or top down. So all 3 dimensions we can utilize here for this metric. And in this scenario, as you saw in the short video, we don't only have one object, we have multiple ones. So we have a moving car, we have a parked car, we have a truck, we have a pedestrian. So we can really employ this for all different kinds of objects. And then this is just one snapshot, but of course we can also do this over time. So calculate this metric over time in the scenario and see, okay, where in the scenario, at which point are maybe problems where there's, for example, occlusion. So one object is occluding the line of sight towards the other object as one reason why maybe the dimensions don't fully line up, or an object is not visible at all. And we can see this directly here in the simulation because we have ground truth. This is the major benefit for the simulation, because in the real world, in real measurements, we usually don't have ground truth data to perform this evaluation. So this is kind of the first part of what we did in this simulation use case, just to show how you can employ metrics to analyze certain algorithms, object tracking in this case. But we also had a second work package here, and this was just to test and improve the interfaces we have. If you remember, we have environment simulation, we have the LiDAR core model, and then we have the tracking attached. And there are all interfaces between those. And our task was to evaluate for the standard ASM OSI interface how it can be used, but also to improve it. And we had 4 major goals here for the improvement of this interface. The first one is to come up with a more flexible support for different beam patterns, because currently the interface is very standard. It's like a pixel matrix, and LiDARs don't work this way. There are different kinds of patterns, so we wanted to improve that. The second one is increased performance, so bring it more towards the goal of real-time capability, increased performance. Third one is that we wanted to implement the sensor view request mechanism that's inherent in the OSI for the first time. And the fourth goal was to make everything open source, well documented, so everyone can use it. So for the first goal, currently, as I said, only regular symmetric beam patterns. There can't be gaps between beams and so on. So we wanted to improve that, and we did. So with our improved version, it is possible, for example, to simulate an asymmetrical pattern. In case of the IBLux, for example, the different layers have different azimuth field of views. So we can implement this now, as you can see in the left picture. Or, for example, the Velodyne VLP32 has layers that are not equidistant in elevation, so it's irregular. And now with our improvements, we can also do that. Or in the case of a Vallejo scala, there are like two mirror sides in the sensor, and you have kind of an overlapping beams, as you can see in this infrared picture from a real sensor on the left. And we can now also simulate this with these 2 mirror sides, as you can see on the right. And the second goal, as I said, was increase performance. So in the current version, you have kind of a fixed TV scheme. So you have pixels in a pixel matrix, which is not really the case for a LiDAR, because some LiDAR beams don't hit anything. So it would be a waste to transfer just zeros there. So we improved that, and we only get valid rendering results over the interface now. And also signal strength and the elevation azimuth angles. So with this improvement, we were able to run the simulation, same simulation, 3 times faster just by changing the interface and improving the interface. No changes in the model, just the interface is different, and we get this big improvement. The third goal, as I said, was to implement sensor view config request. That means that from the model itself tells the environment simulation basically what it needs. So what kind of ray tracing it needs, which rays in which direction needs to be shot. And we did a first proof of concept in our modeling frameworks, or general modeling framework for our simulation models is capable of doing this. And the counterpart was provided by DSpace in the first test version to basically receive the sensor view request and put it into motion. So there's an instantiation step where the FMU is instantiated and tells basically the application what to do, what sensor pattern to use. And so for the user, this is then done automatically. And the fourth goal, put everything open source, documented well. We did that. The LiDAR model and also all other models, all other sensor models are published open source. The link is here on the screen. Feel free to check it out, comment it, download it, test it with your system. The documentation is there to connect it to other environment simulations. And it is fully supported on the set level OSI. This is also open source. So as a conclusion, all 4 goals were fulfilled with the performance and general OSI enhancement. As an outlook, what's next going to happen is a sample validation of this model. So really comparing the model to real world data. This is done in the VB methods project. There will be also a separate presentation on that. And currently our changes to the OSI interface are only in the set level proprietary version of OSI. So the next step would be to bring all the improvements to the standard ASAM OSI 4.0, which is already going on. There are discussions about it. So this will be next. Thank you very much for your attention, and feel free to ask any questions.